1, 2, check 1, 2. Is this thing on? Okay. All right, lesson 3. Rectangles, rhombuses, and squares. Oh my. All right, 6, 4, 6, 5. So we've learned about different types of quadrilaterals so far. We're getting a little more specific, a little more special. Let me move this out the way. Oh, I can't get that. Okay. Rectangles, rhombuses, and squares, and I'm sure you've heard about these before. Maybe rhombus is the one you've had the least experience with. Here are the 3 definitions of those terms. Rectangle, I'm sure you've seen a lot of rectangles. You're looking at one right now in the shape of this screen and this YouTube video and all that kind of stuff. And the piece of paper. Quadrilateral with 4 right angles. That's technically the definition of a rectangle. All you need, if you had to prove something was a rectangle, all you need to prove about it is that it has 4 right angles to meet the definition. A lot of other properties that it has, and we're going to get into those in this video, but the definition technically is just 4 right angles. That makes it a rectangle. Notice it just says a quadrilateral. It doesn't require that it has to be a parallelogram first in order to meet this definition. That's a property that we will show that has to be true, but they want to make the definitions as simple as possible to meet and still be specific enough to only speak to rectangles. Rhombus, same thing. It starts with a quadrilateral that has 4 congruent sides. So that's all you need to have to be a rhombus. Of course, then there's properties that follow, such as being a parallelogram, etc. And square is both those things. It has to have 4 congruent sides and 4 right angles. So what I talked about before about them being parallelograms is a property, sort of a spin-off, sort of a consequence of all these definitions. If you meet any of these definitions, you're also going to have to be a parallelogram, but it's not required in proving the definition, or proving it by definition, which is going to save us a lot of time. Excuse me. All right, so here's some theorems about those things. Here's some other properties other than being parallelograms in the first place. First one is if you've got a rectangle. Now, they probably didn't even have to use the word parallelogram here. They could have just said quadrilateral and it would have been okay. If you have a rectangle on your hands, then the diagonals are congruent. There's a property of rectangles. It's pretty easy to prove. It says JL is going to have to be congruent to KM. They have to be the same length. This entire length here has to be the same as this entire length here. I'll get into proving that if I have to, but I won't if I don't, and I hope you're all right with that. If you're not sure why that has to be, ask me and I'll be happy to prove it to you. Diagonals of a rhombus. Well, first of all, we didn't really show a rhombus on the last page. Rhombus is anything that has 4 congruent sides. Notice they showed the 4 right angles here. Why didn't they show the 4? All right, so if it's a rhombus, it has to have these 4 congruent sides. If it has 4 congruent sides and you draw the diagonals in, these diagonals have to meet at a right angle. So that's the big so what here, is that we have 90 degrees here at the intersection of the diagonals. Another one about diagonals of a rhombus. Notice it has 2 parts. Not only are the diagonals perpendicular to each other, but again, this is a rhombus. Why didn't they put this in here? All right, if it's a rhombus, then the diagonal bisects a pair of opposite angles. So in other words, 6 and 5 are congruent, 7 and 8 are congruent, 1 and 2 are congruent, 3 and 4 are congruent. This is happening at every single corner. I'm not going to mark them all in, but this is happening everywhere. Okay, and they wrote out the which is which there. 2 more. Notice we're up to 20 theorems from this chapter already. Oh my gosh, this is only the 3rd video. Well, there's not many more, but still, that's a lot. All right, if 1 pair of consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. Yeah, here they kind of had to say parallelogram. All right, so if you've got a parallelogram and you know that 2 neighboring sides are congruent, well, we already knew that opposite sides are congruent, so I already knew that AB had to be congruent to DC, BC has to be congruent to AD, so guess what? Transitive says they're all the same, meaning we've made it to rhombushood. Little red rhombus hood, to be specific. No, just kidding. All right, so if a quadrilateral is both a rectangle and a rhombus, then it's a square. Well, if you look back at the definitions of those 2 things, if it's a rectangle, it has 4 right angles. If it's a rhombus, it has 4 congruent sides. Well, then guess what? You've met all of that. So you have to be a square. I made this really big on here to emphasize this point. We made it so that all this stuff, these theorems you've just seen so far on this page, or in this video, a lot of these are if and only ifs, or a lot of these are sort of forwards and backwards. We've made them all into biconditionals. because the other version is coming up later in the chapter. If a parallelogram has diagonals that are perpendicular, then it's a rhombus. If it's a rhombus, then its diagonals are perpendicular. That's going to make your life simpler if you haven't noticed that already. All right, so now because of all these properties and all these different definitions of different types of special quadrilaterals, they're giving you they're giving this Venn diagram to give you some techniques for how to memorize what goes with what, or how these things kind of belong to each other, or sort of subsets of if it's what type of figure, then it's what else type of figure. So they already just said in the last theorem that if it's a rectangle and a rhombus, it must be a square. So that's kind of what this is trying to illustrate. So here's the set of all parallelograms represented by this box here. So parallelograms can exist outside all these definitions of rectangles and rhombuses and squares. This is neither a rectangle nor a rhombus. This is neither a rectangle or rhombus, and it's perfectly fine to be a parallelogram that's not in either one of those clubs. But if it's a rectangle, it could be a rectangle that's not a square, fine, plenty of examples of those. It could be a rhombus that's not a rectangle, yeah, plenty of examples of those. But if it's both a rhombus and a rectangle, then it has to be a square. This reminded me of something I created. Now this is not on your page, and we haven't talked about all of these yet, so I'll be showing this later. The part I want you to focus on really is just kind of this part of it. It's saying that the way this hierarchy chart kind of works is that all these things are called quadrilaterals, and they get more special as you go down the picture. So if it's a quadrilateral, it might be a parallelogram if it has all four parallel sides like this. If it's a parallelogram, it might be a little more special in being a rhombus, in that it's going to have four congruent sides, or it might be special in the fact that it has four right angles. If it has both those things, or either way, sort of down this path of specialness, it could be even more special and be a square. The way this, I think, is kind of valuable, then if you read this upwards, it's like, well, then if you know it's a square, it has to be a rectangle and it has to be a rhombus. If it's a rhombus, it has to be a parallelogram. If it's a rectangle, it has to be a parallelogram. If it's a square, it has to be a rectangle and a rhombus, therefore it has to be a parallelogram. So I like the up and down nature of this type of organizational chart, but again, this isn't in your worksheet in front of you. You can pause and copy this now, this is no problem. I'll come back to it when we have these other things to throw into the organizational chart in probably the next video. All right, so ready to do some actual algebra here. Find the measure of y in rectangle. Ooh, okay, they said rectangle, so I can think of this now, just because they said rectangle. All right, if JP is 3y minus 5, and MK, that's this whole entire thing, is 5y plus 1. Well, what's the relationship here? JP, well, this is a parallelogram, right? Because it's a rectangle. Remember, rectangles are parallelograms. Rectangles all fit inside the world of parallelograms, or if you're like this, rectangles are below parallelograms. And parallelograms, you remember from the last couple days, P is the midpoint of both of these things. So if JP is 3y minus 5, PL is also 3y minus 5. So I know that 3y minus 5 times 2, or 3y minus 5 plus 3y minus 5, has to equal, since it's a rectangle, has to equal the other diagonal, 5y plus 1. So I used the parallelogram theorem there, and I also use, overall here, a rectangle theorem. Then I'll do some algebra and find out that y has to be 11. Find the measure of y in rhombus. If JFK, that's right here, this is 6y plus 7, that's degrees. And if KFG, that's this one over here, is 9y minus 5. Well, we had a theorem about rhombuses just a minute ago that said these things have to be congruent. FH bisects the big angle at F because it's a rhombus. Not only that, that was a right angle, no consequence here, but that's what's going on. So I know these things are equal. 6y plus 7 has to equal 9y minus 5. Algebra time, and bam, y equals 4. Okay. All right, use the slope formula to determine, okay, big hint, use slope to determine if this thing is a rectangle. All right, if I'm trying to determine if something's a rectangle, yeah, I got all these coordinates and that's great. I'm going to use those, but what am I going to do with them? Am I going to do distance, slope, or midpoint? Those are the three big things we always do with coordinates, remember? If I'm looking for rectangle, remember that the definition of rectangle is that it's got right angles. So if I'm looking to see if something's a rectangle, I got to see, are these things actually perpendicular or not, and that has to do with slope. So let me draw it out. All right, something like that in my appropriately badly drawn diagram. I want you to see how bad this is because I don't want you to rely on how close it looks perfectly on the graph paper if those are perpendicular or not with your protractor. I want you to think about the numbers. So I need to actually find all four of these slopes, or at least keep looking at consecutive slopes until I'm convinced that it's a rectangle or not. So I don't know, since J's up here in the corner, let's determine if this is a right angle or not. So I'm going to try to find the slope of JM, and I want to use the slope of JK, and I'm being serious. Okay, slopes, remember you always do this sort of subtraction fraction business. Slope of JM, all right, J is negative 10, 2, so let's put that in as negative 10, 2, and the slope, and M is 2, 5, we'll put that in as 2, 5. And so I get negative 3 over negative 12, which is positive 1/4, be careful. Slope of JK, J again is negative 10, 2, ooh, sloppy fraction bar, and K is negative 8, negative 6. So 2 minus negative 6 is 8. Negative 10 minus negative 8 is negative 2, so this is 4. So the big question is, are these two perpendicular? And, whoa, sorry, that was negative 4. And the answer is, because I just made that fixed, let me make that more obvious because you're going to look at this later and want to be sure. Okay. The answer is yes, those are actually perpendicular. So let's put that in. That yes, we have a perpendicular corner here. 1/4, and negative 4 are actually perpendicular. Let's keep going. Let's look at JK and KL. Well, I've got JK already. Great. Don't need to do that again. Slope of KL is, all right, what's K? K is negative 8, negative 6, and L is 5, negative 3. Negative 6 plus 3, I get that. Negative 8, whoa, looks like we have a problem here, Houston. This is, well, positive 3/13. This is not perpendicular to negative 4. Also, remember, if this is supposed to be a rectangle, KL ought to be parallel to JM, and it really is not parallel to JM. It's close, you know. 5, negative 3, and yeah, see, it almost, if this would have been if this would have been a 12 down here, we probably would have been okay, but nope, it's not. So we do not have perpendicular here. We don't have parallel here. This ain't no rectangle. Okay. All right. I don't know if you've caught this yet, but by now this should be kind of obvious that when you see a bunch of problems like this in these boxes and these grids at the end of these notes, you can be pretty sure these are going to show up on a test. Happened with Are These Triangles Congruent? Happened with some other stuff in the last unit. Sorry, I can't remember right now. It's going to happen with the parallelogram stuff from the last few sections. It's happening right now. All right, what's the best name for this thing? Well, it's got diagonals that are, you know, all sort of the same distance emanating from here. So not only is this going to be the midpoint of both, ooh, danger, danger, midpoint of both, that means it has to be a parallelogram. Yes, you're right. But also, these diagonals, since they're both one tick, and one tick, they are overall the same length. That, to me, looks like rectangle. Overall same length, and they bisect each other. Okay, great, rectangle. Anything better than that? Well, if you're trying to think, okay, rectangle, could they be any better than rectangle? I like this again. Rectangle at least. Could it be a square? Like, once I've gotten to rectangle status, I know I'm already past parallelogram. If you look at this, once I'm in the rectangle club, I know I'm already in the parallelogram club. Do I need to go as far as square? Is there a better name out there? Is square going to tell me what it is? Do these have to be a square? I don't know. I think maybe the easiest way to decide is see, could we draw this as a rectangle that's not a square and see if this stuff is still true? Whoa, that's a really bad picture. Turns out, yeah, if it was a rectangle, this stuff would still be true, but it wouldn't have to look like a square. So I think we're stuck at rectangle, as bad as my picture is. Oh, I'm going to have to go on to part 2. I promise part 2 is going to be short. In fact, why don't I just stop right here? We'll pick up part 2 here at part B.